You know when you're scrolling through Netflix and you just wonder, how does it really know what I want to watch next? Or, how Spotify just magically pulls that perfect song out of thin air? Yeah, these recommendation systems, they're everywhere. But let's be honest, they're far from perfect. So today we're going to dive into a really powerful new AI technique that's designed to make them a whole lot smarter.
Okay, so here's the game plan for today. First up, we're going to meet the new kids on the block, these next-gen recommenders. Then, we'll dig into a pretty major problem that's been holding them back. After that, we'll break down the 3 biggest hurdles that have really stumped researchers. And then, we'll get to the good stuff, a surprisingly clever solution called A-SFT. And to wrap it all up, we'll see what happens when we put it to the test.
All right, let's kick things off. We're talking about where recommendation engines are actually heading. And the big idea here, it's all about moving beyond systems that just, look at your past and try to copy it.
So this new wave, it's called Generative Recommenders, or GRs for short. And honestly, the best way to think about it is to think about the magic behind something like ChatGPT. Yeah, it's that same kind of powerful AI. What these models do is they look at your entire history. I'm talking every show you watched, every song you played, and they treat it all like a continuous story. Their one and only job, figure out what comes next on the next page.
Yeah, that's a perfect way to put it. It's basically autocomplete, but for your tastes, right? Just like your phone tries to finish your sentence, these models are trying to predict the next movie you're going to click on. But, and this is a big but, there's a pretty big catch.
I mean, what happens if the model is just imitating a choice that you ended up regretting? See, a system that only copies what you did before without understanding what you actually liked, well, it can send you down a really, really wrong path.
Okay, for example, and we've all been there, right? You try that super popular trending show everyone's talking about, you watch the first episode, and you absolutely hate it. Well, a simple imitation model just sees that you watched it and thinks, oh, great, they must want more shows exactly like this one. It totally misses the most crucial piece of context, that you didn't actually enjoy it.
And that right there, that brings us to what researchers call the post-training problem. Because if just copying us isn't the answer, then how do we teach these models what we really like? Well, as it turns out, that is a surprisingly tough puzzle to solve.
The whole goal here is to use all that rich feedback we're constantly giving, the obvious stuff like star ratings, but also those subtle clues, like how long we watched something. The idea is to use all of that to fine-tune the model to transform it from just a simple copycat into a genuine preference engine.
Now, I know what you might be thinking. Wait a second, don't we already do this? Don't we fix AI models using human feedback all the time? And yeah, you're totally right. With large language models, there's this technique where people basically give a thumbs up or a thumbs down to the AI's answers to teach it what a good response looks like. But, and this is key, trying to use that exact same playbook for movie recommendations, well, it runs into some really unique and kind of thorny challenges.
So what exactly are those challenges? Well, that brings us right to our next section, the 3 big hurdles that stand in the way of building a truly better recommender system.
Okay, so first up, there's this thing called a lack of counterfactuals. And all that really means is you can't ask a Netflix user to sit down and rate 1,000 movies they've never seen just to get data for your model. It's just not practical. Second, the feedback we do get is super noisy, which is just a fancy way of saying it can be really misleading. And third, the original system that made the recommendations in the first place, it's often a total black box. We don't know why it recommended something, which makes it really hard to fix its mistakes.
Let's zoom in on that noisy reward problem, because this one is absolutely crucial. Just think about watch time as a signal. A system might look at the data and assume that because you finished a 3-hour movie, you must have loved it. But come on, maybe you just fell asleep on the couch, or you were stuck on a 10-hour flight with nothing else to do. Watch time just doesn't always equal satisfaction, and all that uncertainty, it makes the feedback really unreliable.
And check this out, this data is just fascinating. Researchers built this really complex, sophisticated model to try and predict user satisfaction. But look at the results. It was barely any better than 2 incredibly simple guesses. 1, just taking the user's average rating for everything, or 2, just taking the movie's overall average rating. The takeaway here is kind of stunning. Even with all this data trying to predict exactly what you'll like, well, it's almost impossible.
Okay, so with all these huge challenges, how on earth do you move forward? Well, this brings us to our next section, and to the hero of our story today, a new method called A-SFT. It's a much smarter approach, and it's all about finding that useful signal that's buried deep inside all that noise. The huge aha moment, the core insight behind this whole new method is right here in this quote. The idea is, okay, maybe the model can't perfectly predict that you'll give a movie a 4.5 out of 5 stars, but what it can learn is that you're probably going to enjoy that movie more than this other one. See, it's not about hitting the bullseye every single time. It's about learning to consistently aim in the right general direction.
And that is exactly what A-SFT does. Now, don't worry about the long name, Advantage-Weighted Supervised Fine-Tuning. Just think of it like this. It acts like a really smart teacher. It looks at your history, and it pays extra close attention to the choices that led to good outcomes. And it kind of just ignores the ones that led to bad outcomes. It's all about amplifying the good signals and tuning out the bad ones.
This comparison here really puts it all into perspective. It's kind of like a Goldilocks situation. On one extreme, you have simple imitation. That's too simple. It just ignores all your feedback. On the other extreme, you have these really complex methods that are way too sensitive. They get completely fooled by misleading feedback. And A-SFT, it's that just right solution, sitting perfectly in the middle. It uses the hints from your feedback without blindly trusting every little detail.
Okay, so the theory sounds great, right? But the real question is, does it actually work in practice? Let's get to our final section and put A-SFT to the test.
So A-SFT wasn't just tested in some quiet lab. No, it was thrown into a head-to-head competition against a whole lineup of other advanced, state-of-the-art algorithms. We're talking about some of the real heavy hitters in the field here. This was a true test to see which approach could actually handle the messy, noisy reality of real user feedback.
And the results? Well, they were pretty darn clear. This table shows how much better each method performed compared to a simple baseline system. Now let's focus on the two most important rows here. Ranking quality, that's basically how good is the list of recommendations, and hit rate, that's did the system actually find a movie you'd like. And as you can see in both of these absolutely crucial areas, A-SFT delivered the biggest improvements, and it wasn't even close. So what's the bottom line from all that data? It's this. A-SFT won on both fronts. See, the other methods, they were pretty good at pleasing the internal scoring system, getting a high reward score, but they didn't actually get much better at recommending good movies to users. A-SFT was the only one that managed to do both. It got the high score, and it delivered way better recommendations in the real world. And the reason it worked so well? It brings us right back to that core idea we talked about. A-SFT was successful because it learned from the direction of user feedback without getting bogged down or overfitting to all those messy, unreliable details. It saw the forest for the trees.
And this all leads to one final kind of provocative thought. Techniques like A-SFT, they represent a huge step forward in building systems that don't just mimic what we've done, but actually start to understand what we prefer. So I have to ask, could this be the beginning of the end for bad recommendations? For all those times you've scrolled and found nothing? Well, only time will tell.